Science Uncut, presented by the Volkswagen Foundation.
Big data is like the Wild West, says VOLKER MARKL. There are no laws and regulations yet. We lack an infrastructure for managing and storing, and we don't even know whether we have enough people who have the skills to handle big data. Big data is hardly ever generated by humans. Machines or sensors provide us with the data, and the sheer mass forces us to change our methods. In making big data useful, quantity plays a bigger role than quality. Statistical analysis beats logic, and we need sampling and storage rather than curation. Syntax has higher priority than semantics, says VOLKER MARKL. All of this requires a new and different kind of statistical analysis. There are few people who have the skills to do this. Most work for big private companies like Google, which leaves academia desperately looking for talent. Big data also has a storage problem, one that is so big it cannot be solved by more bandwidth. Genomics, for example, generates so much data it cannot be stored anymore. It's simply too big. There's a lot of hype about big data, admits Markl. But that hype is rooted in reality. How we manage the challenge will shape the way we do business and science in the future. In his talk, Markl explores the biggest challenges posed by big data from a technological perspective. VOLKER MARKL is a computer scientist and technologist. He is professor and chair of the Database Systems and Information Management Group at the Technische Universität Berlin. The title of his talk is Big Data and Challenges for Research and Research Funding. He gave his talk on March 27, 2015 in Hanover at the Herrenhausen conference Big Data in a Transdisciplinary Perspective. The conference was organized by the Volkswagen Foundation.
Thank you very much, and I'm very happy to be here. So I am a computer scientist and technologist, but when hearing about big data and all the diverse areas, one can very clearly see from the talk during the last couple of days that big data is on the one hand very complex, on the other hand it's very diverse. And if we listen not only to the talks previously by our colleagues from the law schools, sometimes you can also get the impression big data is a big mess. So let us maybe look back and first see some part of history. So who were some of the people who got us into this big mess that have to take some of the responsibility here? So those are actually three pioneers in the area of data management. So I'm from the data management field. And in data management, we have been dealing with actually big data for a long, long time, according to the various definitions that have been offered here. So big data or data management, it's always about dealing with large amounts of data. What large is, of course, depends on the time and on how it was generated. And here are three representatives. One of them was actually quoted or cited during previous talks already. So the first one on the left is Ted Cott, who really invented the relational data model, the standard way of how we nowadays think about analyzing data. The second one was Jim Gray, who actually has been working to a large amount on transaction processing next to all this work on this low-integral Sky server and so on. And the last one is Mike Stonebreaker, who worked a lot on systems in the data management space. And all three have in common that they have, the according years that you see here, won the Turing Awards, which is the Nobel Prize in computer science, right? Computer science is a fairly new field, so we don't have a Nobel Prize, but we have the Turing Award, which is essentially the same thing. And so it's just interesting because Mike Stonebreaker just got the Turing Award. It was just announced 2 days ago. And but if we look at what big data management did, if we look at the history, then first one important statement to make: the computer industry, and that's a word of Larry Ellison, the CEO of Oracle, the computer industry is more fashion-driven almost than even women's fashion. So that's what he was essentially stating. So we always are finding new trends, new buzzwords to follow. And what you see also on the very top here is a hype curve. This is a hype curve that's following the Gartner hype cycle. So Gartner always publishes this hype curve, which essentially says there's a new word, a new buzzword, a new trend that is incepted. At some point of time, it reaches this peak, which is what's called the peak of inflated expectations. Then there comes this trench of disillusionment, where we all realize, oops, it promised way too much and it cannot really deliver. And then there comes the enlightened adoption, where we see actually there is some value of the technology. And if you look at the Gartner hype cycle, big data is right now, as we all can imagine, pretty much here at the top. However, that's not the first time that a hype is going through that hype cycle. Obviously, in data management, we have had many of those. And this is just an example of several of those hypes that I've drawn up on this chart from relational databases, which really revolutionized data management. But of course, there was some hype, but they are widely adopted, to parallel data management and data warehousing, to open source database systems, columnar systems, very trendy. Actually, during the last decade have been so-called NoSQL systems. So SQL is this language that one uses to interact with a database. And the interesting thing is this language has some limitations I'll get to in a bit that force us to rethink things again. And now there are some alternative implementations on that. But essentially, all of those have followed this hype cycles, and we're in that as well. That said, big data is a hype, but at the same time, there's also some reality here. And we've heard a lot about this already during the last days, that of course more and more data is available to scientists and businesses, and the key drivers here are a large amount of data generation that's happening in cloud computing, Internet of Services, Internet of Things, and cyber-physical systems. Because of high connectivity, large amount of collaboration, and a large amount of computer-generated data. So the observation is that big data is hardly ever generated by humans. It's almost not possible, because if it's generated by humans, we don't scale well enough to generate big data. So it's generated by machines, by sensors, and so on. And there's a huge amount of applications. We've heard about many of those during the last days in the sciences, at home, in the businesses. And we see that those will have huge impact on how we do business and science in the future. But the key observation, and we have been talking about the definitions of big data for quite a bit, that data and analysis are becoming more and more complex. So it's really, that's what I would like to highlight. It's all about the complexity that we are facing that has changed. And people have talked about the 3 V's for a lot already, which is kind of a funny way of characterizing big data, by the way. So this was actually something that Gartner used, right? So velocity, variety, and or variability, and volume. However, that's not really the key problem that we are facing. So that's the interesting thing. So those 3 V's deal with what in data management we call scalability. It's about dealing with massive amounts of something. And guess what? Data management has done that for more than 40 years. And systems like, Teradata, the CTO of Teradata, Todd Walter, told me they easily can handle petabytes of data. One doesn't need so much of new technologies for that. And also as long as the analysis that you're doing on this data is simple enough, and by simple enough, I mean the traditional business reporting and asking questions in semi-structured or structured way using query languages like SQL, XQuery, or also Sparkle for RDF, or doing data warehousing by loading data using this popular concept of MapReduce that people use very much in a technology called Hadoop. But this is actually solved problems. So those things actually work fairly well. What we are seeing in big data and what's really making a change now from a technological perspective is that there's 2 worlds coming together. Namely, this world of data management that dealt with scalability by giving structure to the data, having simple structures in data models, and doing analysis. That comes together with the world of much more complex algorithms on the analysis side. And this much more complex algorithms come, and we heard that already also on Wednesday, from the world of predictive and prescriptive analytics. So we want to make predictions, and those algorithms cannot be expressed in those fairly scalable languages like SQL and XQuery anymore, because those languages, SQL and XQuery, they follow a mathematical concept called the relational algebra, a very deep-founded concept that is very powerful for analyzing data sets, but it's also limited. The key thing is we are using, for those predictive analytics, data mining applications, we're using essentially algorithms that are iterative, so that loop over data multiple times. Traditional data management was designed to go over the data only once, but now we are looping. And this looping over the data, if you want to read a petabyte of data multiple times, this really breaks many, many systems. And the key challenge here is now we are having those two worlds coming together because those non-trivial data analysis methods like clustering, classification, and so on, they work fairly well on small data. They work on data that fits into memory. And that's where systems like MATLAB, R, or Python are used to analyze that kind of data. But once the data gets large, those systems break. And this is a technology problem. And at the same time, there's a problem. What big data means is a shift for using this more complex, more deep analytics in contrast to traditional data management. Actually, we are seeing a wild, wild west out there, right? So we saw wild west in the legal space. Thomas and others explained that very well. So there's a lot of uncertainty here, but also in the way we deal with the data. Because, and that also to some degree was covered, as I understand, on Wednesday already, but sampling and storage are really the key, not curation. So big data is not about curation. Big data is about sampling and storage. And the challenge is you don't know what to store, and can you even store all of it? So that's the challenge. It's about quantity, not about quality. So the hope is that through quantity, we get a new quality. And it's about statistics over logic. So instead of using logical calculi to reason about the data, we use probabilistic models with statistics. And at the same time, it's about syntax, because we don't have a semantic data model. It's about syntax instead of semantics. In that sense, it's really changing how we deal with the data. And if you were used to interfacing with data and you take the data for granted, that's exactly the truth, because that's the assumption in relational databases. That's not true anymore now. We're dealing with probabilities. We have to worry about confidence. And we have to worry about, making the right conclusions out of the data, not to confuse essentially correlation with causation, right? This is a very common theme. So in this way, we have the West, the new Wild West here, simplified by much more chaotic large data sizes, the math rules, whereas the more structured traditional way of how data is managed, like if people work with RDF or people work with SQL or so, which is very well structured. So that's the change. And we are using machine learning methods and others to get insight. One challenge in this world is actually that often data is too large to store. So I'm not sure if we have talked about that yet, as I missed the talks yesterday, but that's the real data problem to some degree. So there was an article in Science in 2011, which said, will computers crash genomics? And it was a major accusation to us computer scientists, me and others, because we are at fault because we don't provide the genome researchers with their tools and abilities to analyze the data anymore. The interesting thing is that if you contrast how next generation sequencing generates new data, if you contrast that to the cost of storing the data, you notice you cannot afford to store the data anymore. So you have to make hard challenges. Of course, this will have huge consequences how we do science, because there is no way to even reproduce anything, right? You have to be smart about what to select, how to move on. So this is big data for real. It's too big to store. At the same time, people talk all about data scientists, right? Data scientists are the people who are supposed to help us to structure the mess of data, help us to gain insight. And the Harvard Business Review said, for instance, that data scientist is currently the sexiest job that's out there. Actually, my statement is different. I would say a data scientist is really a really poor person. And the reason is that if you look at what a data scientist has to know, what I have drawn here, data scientist has to have 3 areas of knowledge. Some people call it, and we heard already, this pie-shaped notion. Data scientist has to know data analysis, essentially machine learning, statistics, and so on. Just some terms from that field, things like that here, like mathematical programming, algebra, and Monte Carlo methods, and so on. So that's in order to derive insight from this mess. On the other hand, since the mess is either big or fast or very heterogeneous, the data scientist has to deal with all those kinds of technologies that goes all the way down to memory management, fault tolerance, and so on. If you work with systems like Hadoop, in order to be able to manage this vast amount of data. And of course, data analysis doesn't happen in an empty space. It happens for a particular application, like in medicine or physics, or you've heard some examples. And in order to build meaningful models, in order to derive meaningful insight, the data scientist actually has to have some kind of domain knowledge in addition. And it's very, very clear that there's very few people that meet those criteria. You have to have the union of those 3 circles. And the problem is, every university pretty much nowadays that wants to jump on the buzzword or a fashion bandwagon is offering data science masters or data analytics masters programs now. Of course, they're bound to fail no matter what to produce the right amount of people, because those skill sets just are not out there in this combination, and trying to educate the people, it's just overwhelming. This is not the right approach. It can help in the short term to get a limited amount of those people, but it definitely doesn't scale. In data management, we're all about scalable technologies, so teaching the people like that is not scalable. Let me do, actually I wanted to go to this slide here. So essentially, the challenge is that data science nowadays still requires systems programming. So in order to apply data science methods like statistics and so on at scale, you still have to know a lot of very deep technical programming skills. And in order to just show this point a bit more clearly, if you look at how many people profess that they have, those red skills, which are the skills in data analysis, I did a count on LinkedIn, one of those professional networks. How many people say they know R or MATLAB, which is kind of a maybe first order approximation for that. You find 3 million people worldwide that say we can do this. And then if you look at how many people know, scalable data analysis, data management, a first order approximation of that is probably how many people say I know Hadoop. Then you find 100,000 people. And really it's the intersection. And that caused, for instance, the Wall Street Journal also to say big data's big problem is little talent. And at the same time, Nelly Cruz, the former European Commissioner for the Digital Agenda, said we will soon have a huge skills shortage on data-related jobs. So this is one of the big challenges we have in big data. So we cannot address the complexity of data science by merely teaching it. We actually need new technologies. So that's a big case of new technologies to empower more people to conduct the deep analysis in big data. And I'll give you an analogy here to database systems, because again, history tends to repeat itself, right? So the interesting thing here is in data management, we had a similar problem until in the 1970s, Cod, the person on the very left on my first slide, invented the relational data model that suddenly enabled us to easily process data by having a declarative language, in this case SQL. So what's interesting is we don't have that anymore. We have lost that ability because in data science, we have to do with iterative algorithms, and we cannot handle this in today's systems. So we have actually moved back 40 years. We are in the 1970s in big data compared to data management. So there's a huge gap in what we need on technology in order to empower people to do data analysis. So this is one aspect of skills. So we have a skills problem. Let me give you another example of a skills problem, and that is a book that maybe some of you are aware of. It's called The Black Swan by Nassim Nicholas Taleb, which is about statistics. Because even if it's not just about the 3 circles, if it's about 1 circle, then in this case the red circle, we have a problem. And the problem is that a lot of statistics courses, including in a lot of those so-called data science programs of many universities, they teach traditional statistics, meaning essentially everything they teach is Gaussian statistics, right? Gaussian statistic means you have distributions where you can define statistical moments like means and variances. The interesting thing is, this is very useful, Gaussian statistics, if you look at some natural phenomena, like the height of us here in the room or our age. Those follow Gaussian distribution. A lot of, phenomena actually do not follow those Gaussian distributions, but follow more long tail or Zipf distribution, like incomes and so on. And the problem is, in those distributions, you cannot in a meaningful way define statistical moments like means or, like averages or variances. And in this case, you need other methods like chaos theory. And what The Black Swan, this book, nicely illustrates, that actually the financial crisis, in this case, the loan crisis and real estate crisis in the US was caused by so-called quants, quantitative statisticians that didn't know about non-Gaussian statistics because they assessed the risk of defaults of loans by traditional Gaussian statistics, which are the completely wrong model for doing this because you have to look at those chaotic distributions. You have to look at chaos theory. But most people in their data science programs don't teach that stuff either. So this is an interesting other aspect of skills. So I'll go back to why we need to simplify life for the data scientist. So we need to have those what we call declarative languages, which essentially means we want to teach people what to write a data analysis program when you want to do a data analysis by just saying what you want and not how to do it. The most simple example of that would be if you want to sort data. In a traditional database system, if you want to sort data, you just say sort the data, which is fine. Sort the data according to a certain criteria in either ascending or descending. this is very different from saying, given a collection, subdivide that collection recursively into collections and do so until your collection only has the size of an element 1. If you have a collections of size 1, compare the elements in those collections, reorder them if one is smaller than the other one, and then recursively move up again. So this is another example of how to sort, but this is a specific algorithm for sorting. In big data, the problem is if we use tools like Hadoop or so on, we actually have to give this specific description of the sort algorithm as opposed to just say sort. And the reason is because we want to parallelize and scale out that, and it really depends, that's the other challenge here, it really depends on what data you're using, how you want to sort. There's many different sort algorithms. Some are good if the data fits in memory, some are good if the data doesn't fit in memory anymore, some fits good if the data is distributed across the network. And the system should automatically decide which of those algorithms to choose, as opposed to leaving that burden to the human. And currently we are leaving that burden to the human, and that's why this multi-billion-dollar market that relational databases has become does not really exist for big data. We have those wizards that do data science, that work for the Facebooks and the Googles, but we have a huge challenge, and I noticed that when talking to companies here in Germany, but also in the US, smaller companies or companies that are not as sexy as Facebook or Google or Twitter, to actually attract this talent. And so instead of writing the how, so which is essentially, it's hard to see on this projector, but here would be 486 lines of code. Here you only have like 65 lines of code, and it's much faster, and it's also much more robust if the data or the underlying information processing platform changes. You still can use it. So that means the deep analysis of big data is key, and what we really want is we have the big data with the 3V, we have the deep analytics, which are, not relational algebra anymore, but k-means clustering and even more complicated advanced methods, support vector machines, expectation maximization. How to do this on big data? This is the question mark in technology. There's a jungle of systems out there. There's many systems, all of them commercial and open source, are still falling somewhat short of that promise. And there's a zoo of technologies. So this is just the Apache open source foundation stack that's centered around systems like Hadoop, Flink, Spark, and so on, that are used for this big data analytics. It's a huge zoo, and it's very hard to actually have insight here. Another part of the problem, going into another tangent, is should it be a federation or centralization? I heard a couple of talks here during the last days, Research Data Alliance and others, that we're also thinking about, how can we actually make data available, right? How can we make those data sets available, assuming that we can store them? The first assumption is we can store them, which again is not always true. But if we can store them, then how should we go about that? The interesting thing is that so far, I would claim that digital preservation has mostly ignored data analysis. So it was mostly, if I talk to people, I'm actually an adjunct professor at the University of Toronto in the iSchool. If I talk to the colleagues there in library sciences or so on, it's mostly about storing and collecting the object. It's not about what to do with them, right? That's usually not the main thought here. And that, of course, is a clear reason why there's a limited success for reuse. So almost all successful data analysis infrastructures actually think about that. And more interestingly, almost all of them are centralized. We are always trying those decentralized approaches here. And the interesting thing is if you look at the really successful ones, they're all centralized. So this is something also to think about in this context. That said, though, can we afford this, right? So, and that's a big question. We don't know, and that's a challenge. So is there basic infrastructure of the data economy or society to have those kinds of data resources? And should those be something that's of public interest, just like roads are or power lines are, right? Do we need something like that in order to bootstrap the data-driven economy, the data-driven society, and in particular for science and research? And then I want to go to one analogy that is often drawn as well and think that to the last consequence. Because we hear everywhere right nowadays, right, data is the new oil. Okay, that's a statement, it's important for the economy. There's a good amount of questions about that because data, of course, is an atypical good. If you look at what Shapiro and Varian say about data, right, it actually is very different from oil. It's very different that it loses value the more you replicate it. You can actually replicate it easily. The value is actually there if nobody else has it. As soon as you share data, it loses value, right? So this is actually a question that I'll ask later on. Is big data value actually opposing research? Or about what does open data have to do with data value, right? There's a conflict here that we have to think about. So data is the new oil. That's an interesting analogy, but if we associate value with it, then we have to look at the atypicality of data. At the same time, if that's the case, then information extraction algorithms are the new drilling platforms, right? So we need to extract information out of that data. The data is Unstructured, the data is messy, it's not modeled, we don't have a nice relational schema or RDF model or whatever of the data. If we have that, then the problem is solved already, but we don't have it, and we cannot even do it as humans because the data is too big. So we need those automatic algorithms to do this stuff. So those are the new drilling platforms. And then integration and analysis algorithms are the new refineries, right? Because they take that and create this higher value out of it. And that means that, we will need something like gas stations. That means we need open information spaces, like if we look at the open data movement, which would actually be the communist approach. Or we say, actually, we are more capitalists, so we want to have information marketplaces where people pay and per use and so on. And those would be the new distribution networks, give the access to the data. And so we have to think about that. First of all, that's the consequence here, and also, is it, which of those ideologies are we following, where and why? And there will be different solutions, different answers, obviously, right? And to take that even further, though, wars are fought about oil. We know that all very well. And actually, we can then predict, and we already see the first sign of that future cyber trade or even Cold Wars will be fought about access to or control of data. So data in the future will be a control point. We see that in some countries and in some economies already. So this will be another challenge for the society, thinking about the oil to data analogy, right? If we think it all the way through. Another more positive side of things, and at the same time also a challenging side, as I already said, because of those complexities of data science, the big problem that we have is that a lot of sciences, and in particular a lot of institutions, are not having access to the data and most importantly to the talent to conduct data science. And the Googles, Facebooks and so on, they can hire those people. But how can we ensure that some important problems that are not of the highest commercial interest will also be addressed? So what I found very great in this context is, this initiative in this case, this fellowship from Eric and Wendy Schmidt at Chicago, but you see some other examples of that coming up as well, for data science for the social good. So we have to think about that. In particular, companies who make a lot of profit out of that should also think about that, so that we are sure that we apply data science to some of the aspects that matter really a lot to society, which, however, would not have the access or the funding to do otherwise. Very important. And that's, I think, also something when we talk about funding. I think this is important. Funding programs could or should go into that direction. The Googles, Facebooks, Twitters that get a lot of attention, in particular in the database conferences, they actually have their own money. This is what matters. So, and now I just want to conclude with a couple of questions that we can or cannot discuss in the panel or also with the audience. I don't have good answers to several of them either, but I think they're worthwhile to be asked. So the first one is, how does big data change the scientific process where we are used to more traditional data management based on logic, semantics, and ontologies, right? That's what we are used to. That's what people do, but that's not big data. In big data, we have to cope with the uncertainty, and how, in this context, do we still ensure quality? Because quality, reproducibility are huge issues. And how can we ensure that the sciences and humanities do not dry out of big data talent when most top graduates in data science get hired by web companies, which is very much the truth. So it even goes so far. I was talking to a statistics professor at Duke University who told me he's not too worried about the NSA and PRISM because actually he knows the people who work there. He educated them. He says, those are not the smartest and the best and brightest ones. The smartest ones are actually at Google. So very interesting. So the next thing there is that, of course, data storage and curation will face a technical challenge in that we have, in some applications, too much data to even store it. Genomics or material sciences being two examples. And how will we have to define, this is now about scientific process again, reproducibility in these sciences? Can we use synopsis, or can we regenerate the data instead of storing it? An interesting idea is, for instance, instead of storing the data on hard disks, store the genomes, so that may actually be better for reproducibility. Then, and a question that I sort of alluded to before already, is open access even viable, right? We talk about open access, but is it even viable for big data? with respect to legal, economical, and societal constraints. So who ensures and pays for the preservation? If we want to preserve big data, this is a huge challenge. This is not your average library anymore. What about privacy? And will we end up with those information marketplaces where only the privileged who can afford to have access will have access, or those data communes where everyone can access the data, having this as a kind of a government role? And it's, in this case, about the storage, but it's also about the transfer of the data, obviously. Some more challenges. So if big data is quantity over quality, syntax over semantics, and statistics over logic, which is what people understood as big data before everybody else started to do it as well. If that's big data, and that's what it always used to be before it became a buzzword, then how do the so far more exact library sciences and the semantic or web or ontology communities have to change? Because obviously those are used, they are on the other side of the spectrum. They are not in the big data space, right? So how do they have to change? Because the truth is always somewhere in the middle. We need both. That's very, very clear. But how do we bring this together? So then research publications are another huge source of big data. We are getting flooded with publications all the time. How can we make this ever-increasing information deluge manageable, right? So using big data technologies for managing the scientific process. We've heard some of that, automatic reviews based on big data that do not require humans to review papers anymore. Things like that, For some conferences with mass submissions, we have to think about some intelligent pre-filtering steps in some cases. So then, I already pointed this one out. Information is an atypical good. The value is higher the fewer people know about it. And thus, the European Union in particular is very big on big data value. There is a huge program, the entire Horizon 2020 program, if you wish, is based on big data value. But does big data value not really oppose the scientific progress, right? Because big data value means I don't want to share. I specifically don't want to share because then it loses the value. So how does that relate? And another one is, of course, maybe we are just too old. Well, I am at least, and several others here in the room maybe as well, in the sense that Generation Y and beyond, they grew up with big data and a large part of it. And they accept it as natural. And most of us here are latecomers, right? And how does this really change society? What does it mean also for laws, right? I mean, so maybe things that are illegal now won't be illegal in the future anymore, right? So things may change. So that's an interesting question. So even though some of the research right now is illegal in some countries, maybe this is just a temporary phenomenon. So, question to think about. Some challenges for research funding that they may also help us in our dialogue later. So many big data projects will be transnational. So that's foreseeable just because of how you arrive at the large amounts of big data. Famous example being the Large Hadron Collider, right, in CERN. So what vehicles do we have for building and maintaining large-scale international data infrastructures given that data is as elastic as a brick wall? So this is a statement that, again, was said by Todd Walter from City of Teradata. He said, big data is as elastic as a brick wall, and what that means is you cannot easily move data around. So transferring a petabyte of data over a network just doesn't work. This is also why cloud computing and big data do not fit very well together unless the data is born in the cloud already. So this is a huge technological challenge, and it's not a challenge that in any foreseeable future the networking community will solve. I mean, you can always say we need higher bandwidth networks, but for big data, it's not clearly foreseeable without a major evolution that will get there. Then, data science requires skills in scalable data management, which is in particular parallel processing systems and databases and programming. At the same time, in data analysis, in particular machine learning and domain knowledge. We heard about this term pie-shaped students already. But how can we ensure the required information literacy to avoid things like, the Gaussian model use in cases where it's not right and so on? How do we avoid this so that people can really make sense of big data? So do we need some kind of data consultancy for non-computer science researchers or non-statistical researchers who may not have those kinds of skills? When I sometimes talk to people in the medical field, I'm sometimes shocked how nonchalant data analysis is done there. In this way, we may have to think about that also in research projects. So how can we ensure that the needed skills and talent are there in some areas that would not necessarily have them? And another important statement is it's not all about big data. big data is a hype. The pendulum is swinging around, right? So big data is important. In particular, statistics are important. Math is important, and deriving that is important as opposed to using logic or semantic web. So big data and semantic web are two very different things. So it's very important to make clear. But actually, big data is not always the solution. Obviously, those other technologies are also important. And so what we have to think about is, so what are areas of research that require those big data methods? And what are the more traditional methods that have been around for quite some time already and still have their justification, right? How should evaluators decide on competing research proposals? Something doesn't get better sometimes just because it's done with big data. If you have semantics, it's very smart to use it, right? As opposed to trying to rediscover it just by amassing data. So semantic may not always be bad. So, and sometimes in the big data community, you have that kind of feeling. Although, on the other hand, it's true that big data opens a lot of opportunities where semantics completely failed, so we have to be very clear about that as well. But at the same time, because of the high commercial relevance, many areas of funding in big data are carried out by companies. So, which means we should look how to avoid double funding, right? There is no need to spend public money when there's a lot of private money there already. And how do we ensure that academia has a chance to compete with industrial research in those cases, I mean, it's hard. Some research, people could argue, can only be done at companies like Google or so on, and it's very hard to do it in the public. And in this context, we really have to think about what can private-public partnerships do here, what role can they play. But the key thing here is actually to have an infrastructure to have access to this data. So Google will not open up easily their data assets, which would be a great opportunity for a lot of research in social sciences and other areas, right? But Google will not easily open this up. So what can we do? Do we need some, again, information space, maybe a more communist-based approach here that makes it available for everybody? Communism is not bad, by the way, right? It's just a question, does it work? If it works, it would be great. So maybe that's the right approach. If we can have the governments agree, it would be a great thing. So what roles can private-public partnerships play? And again, also for the research funding here, with all the focus on big data, we must not forget to still keep a focus on little data. Little data also matters. That is, how can we make sense of few observations or the long tail? So the problem with big data may be we may get into the tyranny of the masses because we are deriving things based on what most other people thought, whereas, what happens in the long tail. So how can we avoid a tyranny of the masses that could very well happen? In particular, if we already see trends of that when we watch TV, right? So, and see how TV programs are being generated nowadays. So how can we find a balance in the current big data hype where, as it seems, only terabytes or more seem to be interesting? I was a member of an evaluation group of research proposals about data management, and people were easily saying, oh, this is just 50 megabytes of data, what's the problem, right? Actually, there can be a lot of problems in 50 megabytes of data. Let's be very clear. That said, in big data, insight may be derived later, so recursively, potentially after a huge investment in infrastructure, like the Large Hadron Collider. So when is it really worth to fund such a project that generates the data? And how do we evaluate the success of such a project? Because the insight may come much, much later, many years after that, right? Should it be the data volume produced, the promised insight? So how would that work? With that, I just want to summarize in my last slide on sort of what we did in this entire workshop here. We essentially, as a whole, and as a society, also have to think about it. We have covered those, what I always call the 5 dimensions of big data. We've heard a lot about law, a lot about those really important and interesting problems on particularly ownership, right? So I completely agree with Thomas Hören. Everybody likes to talk about privacy, but you know what? Privacy is maybe not the biggest challenge, actually. Ownership, copyright, there's others. There's a huge amount of societal problems, right? And I already mentioned, public good. We have to really start to think about how can we use data analysis here. There's a huge amount of changes happening in the business world, with new models about information pricing, open source and open data movements, right? Information marketplaces. What about benchmarking? And of course, lots of things in technologies. I myself am a technologist. I'm actually building big data analytics platforms. So my my research focuses on making sure that you can analyze petabytes of data. So personally, I'm not interested in the megabytes. But that said, from a research perspective, with my actual research, but that said, let's not forget about that and also all the related technologies there as well. And of course, there's a huge amount of aspects in many different verticals and domains. Overall, I began, and SJ was comparing it to the Wild West, right? So big data is the Wild West. It's in many dimensions. We have legal problems, people ignoring the law, exactly what happened in the Wild West. We don't have the infrastructures yet, just as we didn't in the Wild West. The roads, the railways were not there. Right now, we are still missing the research infrastructures. We are missing the networks, but most importantly, the access to data and the data analysis infrastructures. It's not just about networks. It's largely also about how can you efficiently at scale run the algorithms. We are missing this in the Wild West, and we are missing a lot of other things. So the hope is, though, that eventually we'll arrive at something like this. This is an image. It's about taming the Wild West. And so I hope that we will eventually achieve that, and then also see, was the Wild West completely the promised land, or is there also not some interesting stuff still in the East Coast? With that, thank you.